Okay, we are now getting into, we got two example problems here of full 3D dynamic analysis here. All right, so that means we're going to have motion that cannot be broken down in just planar motion in terms of the full motion of the system. And we're required to then work through all three dimensions, right? But we're always looking for ways to simplify that 3D analysis and make it as straightforward as possible, right? So we're going to take our ugly moment Euler equations that really represent the moments and how that causes angular acceleration, and try to make that as nice as possible. Okay, so we're going to take this system here, 9 kilogram disk that's spinning, right? And so it itself, right, with just if we just had that system right there, that would be planar motion, right? Meaning any point on the disk as it rotates, it's actually rotating that way, as it rotates is staying in this plane, right? Or if we just took what's over here and we just had a like a base with like a rod rotating, right? I'm trying to hide the disk, so there's like a rod here that then rotates. Any point then on the rod, right, would be in planar motion, right? It stays always in that like horizontal plane here. Here it's staying in that vertical plane. But, you know, why this is true 3D motion belongs here at the end of the class is we got both of them at the same time. All right, so that means that if the shaft AG is rotating about you know, the primary vertical axis here, and I'll label these primary, secondary, and the body here in a second. So if we have that rotation and then we have the additional rotation of the disk, think about a point on the disk. As it rotates, yes, it's going to go further down the disk, but the whole disk itself is now moving in this direction. So these points are then like wrapping themselves in all of three-dimensional space. So let's label all of our like reference frames here. Obviously, maybe not obvious, but the primary is now this base. Okay, the body. Let's go in order. So secondary is then, well, no, let's go to the body, right? That's like the furthest down the line from the primary. So how many, you know, rotations we have to get there? All right, so the body is then the disk, and the intermediate rotational element here is the oh, I'm holding it in my hand. I was looking for the purple here to keep it consistent with our earlier coloring, and it was in my hand. Is the AG axle. Okay, we are given this to be 20 radian per second. We're given the geometry of the system here. What we want to determine is the omega 1, which is the rotation of the axle, that keeps the system horizontal, keeps this perfectly horizontal as it rotates around. All right, so there's going to be some combination of this motion here. Think about that, right? The point G itself is then in uniform circular motion, right? And who cares about the disk around it, right? Point G just kind of wraps around in uniform circular motion, right? Well, A could, you know, be, moving all over the place here, but yeah. Yeah, we're just looking for the omega to keep this perfectly horizontal. Okay, so let's go through our procedure. So the first step is to look at the geometry, and we're looking for a principal frame. Okay, and now and in all of our analysis, we're going to fix a reference frame to the body, and that's what we've done here, right? The XYZ coordinate is now fixed at G, so that as this rotates around, right, the whole system rotates around, the reference frame moves with it. And then our equations adjust for that, right? We have, when we get to kinematics, we'll see how that adjusts for that, right? But that coordinate system is actually in the problem statement here, XYZ, is a principal frame, meaning that there is a rotational symmetry about the y-axis. In fact, it's for the whole axle combined with the disk, right? That is that whole axle disk system there is rotationally symmetric about y. You could rotate this as much as you want about this long y-axis, and the picture is not going to change. So we have rotational symmetry about our chosen y-axis, or maybe it was imposed through the problem statement, through G, through the center of mass of the disk, of the body. Okay, so because rotational symmetry, we know that all of our products of inertia are going to be 0, and that greatly simplifies those equations of motion when we get there. Okay, all of those are 0. It also tells us that the moments of inertia about the other axes that aren't the y-axis have to be equal to each other. And a quick look up in the table tells us that this is 1/4 mr squared. Right, Appendix C, just look for the circular disk. And then Iyy in that same table is just 1/2 mr squared. Okay, so we can actually go and calculate these. Okay, so let's do this here. So this then equals 1/4 times the mass is 9 kilograms, and I'm going to write this in meters. The radius is 0.24 meters, or 240 millimeters. That's squared. So this turns out to be 0.1296 kilogram meter squared. So that's I about the x-axis and about the z-axis as our moments of inertia. And then this one, well, we just notice here you just have to multiply this by 2. Well, we'll write it all the way out. But, right, this is 1/2 times 9, 0.24 squared, which turns out to be twice that, right? 0.2592 kilogram meter squared. Great. All right. Right. So we found our principal frame. I think I've been saying principal axis. Okay, principal frame of reference, which is, well, the chosen one, because all of our products of inertia drop out to 0. Okay, now we're into step 1. I don't know why we just don't call it the geometry step 1. Okay, that is drawing a free body diagram. Okay, so we're going to do this for the entire axle disk system here. Draw out all the forces there. Okay. Oh, and I should mention here, because we're getting in the free. Okay, let me draw this out, and then we'll make a comment about what's happening there at A. Okay, let's put G right there, and we'll get the circle. I'm trying to kind of match the diagram. It kind of looks like that, kind of at an angle. I don't know. I didn't succeed that well. Okay, here is G. Here is A. Now this, in the problem description, says this is a ball and socket. That means that that point A can't move anywhere. It's locked there, right? It's like a socket wrapped around a ball, right? Okay, and so you can't move anywhere, but you can rotate all you want, right? In any direction. There's free rotation. We're not restricting rotation, but we are restricting movement in any direction. So when we write the forces on this object, let's first put the reactions. Okay, so the reactions up here, if we're restricting motion in any of these directions, but we are allowing rotation, well, there's no reaction moments at A, but there's a force in every direction. So we've got AZ. Oh, and I need to put the coordinate system on here. So let me get these on here first. AX, since we're talking about it. Now let me put the coordinate directions. Okay, so this is our y-axis. Okay, there is z, and there is x. Okay, now let's see what else. Let's also put our, I always like to put our unit vectors then, because we're going to be doing a lot of cross products as we go along here. This is going to be kind of the diagram we refer back to quite a bit. So I like to put our unit vectors in there just to remind ourselves what those are. Right, and they just go on the x, y, z is the I hat, j hat, k hat. And then we missed one force, which is just the weight. Other than that, there's no contact forces, so therefore there's no friction. This is just m times g, and that's it, right? Okay. Next step, I'll use the space over here, is the kinematics in our general procedure. Okay. What we want to do is determine omega 1. So it'd be nice to have a relation to that, to the quantity we do know, which is omega 2. The way we do that, right, is through the way that these rotations, these angular velocities relate. You know, that's kind of the new bit in our kinematics here, right? What this says is that the rotation vector of the body, okay, and I'm not going to be able to put the b there, is the rotation rate of the secondary, which is the AG axle, plus the relative angular velocity of the body with respect to the disk. So let's label all these. This is body, secondary, body with respect to disk. So this is the disk. This is the, and now this is the disk written in, with respect to primary. So O here. This is our AG axle, and then we have disk AG. Okay. And now let's see. Well, what is that? So then omega equals omega 1 k hat plus 20 j hat. Okay, so if we ever need to plug in omega, which is the rotation of the disk, it's going to be this rotation plus the 20, right? Now that is the rotation with respect to the axle, right? With respect to the secondary reference frame, as if you were an observer standing here looking down the shaft, right? Observing the rotation at the end, right? Okay. So I should say that observer is in the secondary reference frame because it experiences the omega 1 movement compared to primary, but it doesn't experience the body, right? And so that's why that's the 20, right? So don't get into this 20 radian per second is an absolute, right? We have to also involve that rotation. Okay, I think that's pretty clear. All right, but this is important. Okay, so this means when we get to our component, right, we're going to get to our Euler equation, right? Here, omega x is then 0. There's no I hat component. Omega y is 20. That's the j hat component. And omega z is omega 1, which is what we're trying to solve for. So it's okay that we don't know that. This is now completely usable in another relationship. Okay, quickly checking that these are both in the positive direction, right? That's in the positive k hat. That's in the positive j hat, as I'm using my right-hand rule to check that. Okay. All right, so we also have a relationship for the accelerations, which we know show up later. So the acceleration, and I'm going to stop subscripting these, instead I'll just say out loud what they are, right? This is the acceleration of the disk. That is related to the acceleration of the secondary, so that's the axle AG, plus the acceleration, angular acceleration of the body with respect to the secondary, plus the cross product of the secondary's angular velocity with the relative angular velocity of the body with respect to s. Okay, let the math do the work here, right? Angular velocity of s is now, the angular acceleration of s is the time derivative of omega s. Well, omega s is just omega 1, which we know to be constant. So that is 0 because omega 1 is given as a constant. Well, we don't know what the value is, but we know it's constant. Let's see if we can find that, right? With constant angular velocity, omega 1. Okay. Also, the 20 radian per second is constant, right? It says constant there, right? Because that's constant. Well, that's what, omega bs is 20. That's the constant. So if we take a time derivative, we get a 0 for this one as well. Okay. This is because the omega disk, as it's given here, is constant. I guess when I say disk, that is disk with respect to AG. So let me sneak that in there. Okay. So it's just these two terms, which we know from the previous up here, right? We already used those quantities. We already determined what they are. No need to think about it anymore. This is omega 1 k hat crossed into 20 j hat. Okay, and k cross j, so here's where I'm using this. K cross j is in the minus I hat direction, and so we get that alpha is minus 20 omega 1 I hat. That's useful, and will be useful when we get to our Euler moment equations where we have those omega dots. These are our omega dots. Okay, those are the time derivatives of the absolute angular velocity. So when we get there, we know that omega dot x is minus 20 omega 1. Okay, omega dot y is 0. It has no y j hat component, and omega dot z is also 0. There is no k hat component here. Oops, omega 1. Minus 20 omega 1 is the omega x dot. Okay, and then the other thing we can do with kinematics is determine the accelerations involved here, right? And so what we'd like to do is use our information that A is a fixed point. Go back to the original diagram, right? A is not going to be moving anywhere. And then relate the acceleration of G to that point. Okay, and that's because when we write out our equations of motion, the center of mass of our body is like where, when we have force equals mass times acceleration, that's, we need to have the acceleration of G. So let's use the information that we have about point A there. Okay, so this is the last kinematics bit. And I'll just keep it nice and organized, but kind of shift over so using a little bit more space here. Acceleration of G is then the acceleration of A. Now these are on the same body, right? G and A on same body, which is the axle. Same rigid body, so we can use this rigid body relationship. Plus the angular acceleration of that secondary reference frame, that's the AG axle, crossed into our GA, plus omega of the secondary, that's GA, crossed into omega GA, crossed into the relative position vector of G with respect to A. Okay, now we look, anything canceling here. Yep, this is a fixed point. Okay, this one we already talked about. Well, this is because omega 1 is 0, so don't need to rethink about that term. This is the only non-zero term here. Okay, so AG, our acceleration of G. Now this is the absolute acceleration of point G. Okay, as it rotates this way, and G doesn't get affected by this rotation, right? It's only going to be wrapping around. So wait, we already talked about this, right? G is in perfect uniform circular motion about point A. Oh, we might know what that is. Doesn't that mean that the acceleration is always inward? Centripetal acceleration? Let's see if that's what we get. AG, we then get omega 1 k hat crossed into omega 1 k hat crossed into, now what is the relative position vector of G from A? Well, from A we just have to go 180 millimeters down the y-axis, so in the j hat direction, so that's 0.18 in meters. So we'll cross this with 0.18 j hat. Okay, now let's do the inner cross product here first. K cross J is negative I hat. So we get 0.1 negative omega 1 I hat. And then we have a k hat cross k hat cross I hat. So k hat, I'm using this like a little k hat cross I hat, that should be in the positive j hat direction, but that negative keeps it negative, right? K hat cross I hat, so that's negative, yeah. Okay. G with respect to A. All right, good. So K, I'm just checking this really quick. K crossed into I hat is positive J hat, but the negative here, yeah, that's negative. Any other reason? Okay. So then this is, oh, and we know it's negative. What am I thinking, right? That is centripetal. I was like wondering, why is it negative? Well, that's because we're going, it's always being pulled inward. Okay, so negative 0.18 omega 1, and there's now an omega 1 squared j hat. Okay, so if we, now that I got over my confusion here, why is it negative? Well, it's negative because the acceleration is always inward to keep G in uniform circular motion, right? About point A. So let's make this a little comment. G is in circular motion about A with a known, well, not a known, but with a angular velocity of omega n. So it's actually uniform because we're not accelerating that angular motion. So g is in uniform circular motion about a with angular velocity of the unknown omega 1 that we want to determine. Okay, just an observation. Now the next step is to use what we have and go to our equations of motion. So we're inching closer to applying the Euler equations. But before we do that, we always start with summing the forces. Okay, and we'll keep our free body diagram close. But I can't probably keep it on the screen, so it'll be right there if we ever need it. Okay, so we sum the forces in the x direction. Only force in the x direction is the ax reaction force. And then that must equal mass times the x component of the acceleration at the center of mass g. Okay, well that, if we go to our acceleration vector, there's only a j hat component there that we just determined, so that is 0. Okay, at this instant, right? And as the reference frames move, as the coordinate system moves with the body, okay, about its center of mass there. Okay, so we just determined, what did we determine here? That there is no x reaction force. Okay, and maybe I'll give it a, that's not our final answer. We're just looking for what omega 1 is, but we're not going to do anything more with this, right? This isn't going to help us anymore, so we boxed it. All right, some forces in the y direction. Well, we might actually use it. Actually, that's not true. We might use this when we get to moments, right? If we're taking moments in this scenario, it might be really helpful to know that ax is 0 so that it doesn't contribute to the moments as we get later on. All right, but it's not a final answer. Okay, summing the forces in the y direction, the only force in the y direction is the ay reaction force. And that then equals the mass of the disk. And note here that the ag axle is negligible mass given in the problem statement. So this is just the mass of the disk, which is 9 kilograms. Mass times acceleration of the center of mass of the disk times, or just the y component here. And this now equals this guy, right? We determined the y component is minus 0.18 omega 1 squared. So minus m 0.18 omega 1 squared. So that means that, well, omega 1 we don't know, but ay we have a relationship for it once we do know what omega 1 is. Mass omega 1 squared. We could plug in the mass as 9 kilograms, but let's just leave it there for now. Okay, and then the next moment of the equation, sum forces in z, right? From just the translational equation, direct Newton's second law, we always have 3 equations of motion for these 3D systems. So here, what are the forces in the z direction? We got an az reaction force, and then the weight, two contributions there. So we have az minus mg, and that equals mass times acceleration of g in the z direction, which isn't no component, right? So that's 0. And that comes, right, no k hat component down here. Okay. All right. Now, let's see. Okay, so then this tells us that az is equal to mg, which we actually know. Okay, but if we need it later, we know what to plug in. Okay, so now we move into the 3 equations from the Euler equations, right? So these are our angular equations of motion. Okay, and what they say is that sum of the moments about g in the x direction equal, and because we're in the principal frame, we have a shortened version of that longer one, ixx omega dot x plus omega y omega z izz minus iyy. And let's just write them all out to be complete before we go any further. Sum of the moments of gy, and the last one is summing the moments about gz. Okay, this is iyy omega dot y izz omega dot z plus. There's a pattern here, so if you know the pattern, you could follow. You can do this without looking at, looking at a version of the equations. Iyy minus ixx. So what I just want to do now is just run through this and, based on our kinematics analysis, cancel things out, right? So we already determined what the angular velocity components and the angular acceleration components are for the body. Those are these values that we have here, okay? So if we just remember, omega x is 0. So anywhere we see omega x, that doesn't mean it's omega x dot is 0. It's just omega x is 0. So that's this term is 0 and that term is 0. So knowing that omega x is 0, I mean, that's all gone. I mean, that's already, you know, hugely simplifying. In terms of the acceleration, the omega dots and the y and the z are both 0. Okay, so that's that one and that one. Oh, look at that. The only thing non-zero is this. So we just determined that we must get some of the moments about the y-axis and z-axis to be 0. Should we start there? Well, let's see. I'm not sure where. Maybe we should start at the one that's actually going to be, you know, helpful, which is the top one, right? Let's analyze that, and then maybe we can come back and visit this. In the end, we should just be able to basically say that there are no moments here. Yeah, let's do that at the end. Let's take these one by one. Okay, so we're going to do this one first, the top one first, the moments about the x-axis. Okay, and then along the way, I think it should be shown why the other two are true. Okay, so if we sum the moments, like, let's actually do all of them at once. Why not, right? So if we look at what the moment vector is about g, right? We come to our free body diagram and we say, well, which forces contribute to the moment there? Well, it's just the ax force that causes the moment, right? And we kind of work through the components here, but like this is just one force vector, right, over here at A. The weight contributes no moment because its line of action goes right through G. So that doesn't create a moment about point G, only the A force here. So one way to think about this is that the moment vector, the only moment vector, is the position vector to get to A from G crossed into that A, you know, with its three components. Okay, well this, we just go backward negative 0.18 in the j hat direction, and then we cross this into ax I hat plus ay j hat plus az k hat, and we look at what those components are. Well, ax is 0, so that one's gone. Az we know to be mg, and then the j hat crossed into j hat isn't going to produce anything. Okay, so the only component we get here is the j hat crossed into k hat, which j hat crossed into k hat is I hat. So we get negative 0.18 az, which is mg, I hat. That is the sum of the moments, and you see there's only an x component there. Okay? So summing the moments, what this says, right, because there's no j hat or k hat component, that means that the sum of the moments, sum of the moments about g, y component of that should be 0. Sum of the moments about g, z component should be 0. Well, that's what we did, you know, we got that up here. So we just confirmed that the right-hand side should also be 0. Okay, left-hand side is 0, right-hand side is 0. Okay. If you didn't get, and now we know what this also tells us, that sum of the moments gx should be minus 0.18 mg, right? Now, there's another way we could have approached this, and I kind of hesitated. I kind of thought about the different ways to do this, right? We could have just said, well, before we did any of this, we could, and that's why my arrow was like pointing down here. I was going to go with this other method first. Like, we could have just noticed like this. These are 0, right? And that might tell us about some forces over here that we want to solve for. But in terms of finding an omega 1, that's just going to come out of this equation. And if we just jumped into that, we would then just ask a different question, which is say, what are the moments about the x-axis, right? And who, because the forces can get more complicated than this, right? What are the moments about the x-axis? Well, think about each force at g here. So again, the weight produces no moment. AY is not going to produce any moment about g because that line of action goes straight through g as well. AZ, think about that, right? From g, point your fingers toward the AZ force, or the AZ component of that force. Wrap your fingers up toward AZ. That points in the negative x direction, right? And so that one contributes a moment about the x-axis, okay? Because that's my thumb from the right-hand row points in the negative x direction. And in fact, I had to go. The moment arm is 0.18, right? And then the AZ force is just mass mg. Right, we already determined that. So that moment is negative 0.18 times mg, which, right, we have here. Now we still have to ask, well, does AX produce a moment about the x-axis? No, right? Go from AG, AX, that would produce a force in the z direction or in the k-hat direction. But remember, we determined AX was 0. So all of these things we're confirming, right? We're basically saying this is 0. Right, we already determined that. This AY produces no moment about G because its line of action goes straight through, and the weight doesn't either, right? Because it doesn't produce a moment either because its line of action goes right through G. The only thing that can possibly produce a moment is the Z component of the A reaction force. Okay, great. We are now very close to finishing this problem. A lot of extra chat about this one. Okay, so now we're ready to go back to our x component of the Euler equation and plug some things in. The left-hand side we determined is minus 0.18, and this is meters, times, let's do it like that, times mass times gravity. So that is, let's just, yeah. Should we write it in? No, let's just do mg. Let's just get it all the way out because I realize the right-hand side we're not going to have things either, right? Okay, so Ixx, we determined Ixx, well, we have a value for that. Let's just write it out here, Ixx. And then because what I want to plug in is what omega x dot is. We determined that here to be negative 20 omega 1 minus 20 omega 1, and omega y and omega z. Those are 20 and omega 1 respectively. So we have plus 20 omega 1 plus 20 omega 1. I just wrote that off screen. And then we have Izz minus Iyy. Okay, which we know values for. So if we're just looking at this, right, we know values for everything except the omega 1 and except the omega 1s there. And actually we're not keeping track of units here, so we'll just plug in the units at the end. Okay, so we can solve for omega 1. Let's get a final relationship for it. Omega 1 is going to be, pull the omega 1s to here, so we'll have a negative 0.18 mg. Divide this by the when we pull these things out. Well, noticing here, all of these terms over here have a 20, so we can pull that 20 out. And in fact, then it's a Izz minus Iyy minus Ixx. Okay, plug in values. We get, now we can maybe be careful with our units because the 0.18 was a distance in our original problem. The mass is 9 kilograms. G is 9.81 meter per second squared. The 20 actually originally came from the rotation of the disk. So that's omega disk, which is 20 radian per second, in terms of the secondary reference frame at least. And then we have values for these, which is 0.1296, 0.2592, 0.1296, and the units here on the bottom for all of the moments of inertia are kilogram times meter squared. And right, so you do the number calculation, we get that omega 1 is 3.066. What are the units? Let's check those separately. We've got a meter, kilogram, meter per second squared. right? Meter, kilogram times meter per second squared. And then you got radian per second on the bottom. So that's just going to put a second in the numerator. And then a kilogram in the bottom and a meter squared in the bottom. Cancel kilograms, cancel the meter squared, and cancel 1 of our seconds. We just get a 1 over second, which is a radian per second. Okay. All right. So that was a we went into much detail over all the steps of this problem. Hopefully, you now see the light that applying the Euler equations is not as ugly as it might first seem, because first of all, we threw a bunch of terms out here just from finding the principal frame, and then even within that, we threw a bunch more terms out. In fact, it only became one useful equation, right? Okay, I got one more example to follow this one. Okay, so in this last example, we have a slender rod. Homogeneous means that it's a uniform mass distribution throughout, labeled as AB here. It has a mass of m and a length of L, split in half L over 2. What I mean by split in half is it's pinned right in the center, at its center of mass, and with what we call a Clevis connection. So and that just means that it. Okay, so what does that do? That means it allows rotation in this way, but does not allow rotation that way, right? Because it's kind of pinned through that, and it doesn't allow rotation that way into and out of the board mostly, right? But it does allow rotation this way. So it's pinned, so its position is fixed, and it only allows rotation in one direction. So that means that there's many reactions here. In fact, of all the reactions of 3 components of force, those are all there. And it has 2 components of the moment reaction to keep it from rotating in those other 2 directions. Right? Only one of those is missing because it does allow rotation up and down. Okay, so instead, this chord is providing that lack of rotation, or preventing the rotation. Okay, what we want to determine is what's the tension in the chord while the thing is rotating with an omega s, and do this all as an expression, right? So we're not given any numbers. We got to keep things completely general here. And okay, so let's start by labeling what our body is, just so we're, when all of our relationships have the first step is to distinguish what is the body. Okay, so the body is the rod AB. Okay, and this is so nice. A B is on the body, which we give that script B. Our secondary reference frame is the thing that's rotating here, right? So that's why I called it omega sub s. That's the omega of the shaft, but it's also of the secondary reference frame. So this is shaft O to C. I'm going to call this point right there C, so it's a point, and know that it's also the G for the slender rod. Okay. So, yeah, that's good. Okay, and then, and then as always, if we're going to label those things, just for consistency here, our O, or our primary, is down here. And so that's what I meant. O is, right there. And that's just our primary. Okay. Let's see, what else do we want to do? Well, we got to put a coordinate system in here before we do anything else. It's going to be convenient now we're gonna fix it to the body, right? So let's have a body fixed reference frame, and so let's have our y-axis go down the long direction. So there's basically the center of our coordinate system. The y value is gonna be down the rod. I think that's long enough. So let's put y there, and then the x-axis will be kind of out at us. So x, y. Okay, so x-axis will be kind of out of the plane here. And then z, if that's the case, now this should be, you know, kind of out at us. So that means z is sort of in the plane here and then perpendicular to y. So that would be right up that way. Okay, so it looks almost like x and y are the same. I could definitely tweak x. Maybe that's more like this way, coming out at us. Okay, those shouldn't look like those are in line with each other. They are actually perpendicular to one another. X is just straight out at us. Z is now in the plane up there. All right, so oftentimes when you write x being out of the plane, you would draw it really short. So maybe that would have helped if I drew x really short. But does that kind of make sense? Right? X coming out, and then y and z are more in the plane of the rotation here. Okay, now let's see. Yeah, let me make that one point. That point C here, just to, this might show up later. Point C is the G for the slender rod. So we might refer to like the moment of inertia or something as G for the rod, and no, those are the same. Okay, what else are we doing? Okay, well we have a yeah, okay, this is okay. Let's move on now. Okay, looking for a principal frame. It's always there, and well, luckily we have a rotational symmetry for our rod. Rods always have rotation with symmetry about the y-axis, meaning that if you go along the y-axis and start rotating the object, well, it doesn't have a cap like mine does, which is non-uniform, non-homogeneous shape or whatever. So, you know, if it's just a rod, it just looks the same no matter what your rotation about the y-axis. All right, now if we took that and rotated it about the x-axis, that would be like, or sorry, about the x-axis would be like that. That is not rotationally symmetric, right? That's a different picture. Or about the z-axis would be, now that's like doing it that way, right? That is also not the same. But if I rotate about the y-axis, rotationally symmetric. Okay, so the coordinates shown, those are my x, y, z that I've drawn them. Those are a principal frame. Okay, and a particular one, well, so that just means that all of our products of inertia are 0. And I, y, y, now this is a slender rod, so this is actually 0. Also, more simplification. And then I, x, x equals I, z, z, and that we can look up. It's a slender rod. And we know that one. In fact, we derived it in class as ml squared over 12. That's just the moment of inertia for a slender rod. Okay. Okay, next, free body diagram. We're just going to do this just for the slender rod. So here's A, diagonally downward to B. C is here in the middle, which is the G. This is what I mean, right? There's the G, which is point C. Don't want to confuse it too much. Okay, now let's see if we can get our axes a little bit better here. So Y is that way. Oh, that's a little bit off the screen. Z then is up that way. Oh, here, let me put Z there. I'm going to overwrite that with one of our reaction forces there in a second. And then X, let's kind of put coming out more this direction. Okay, oh, and again, I'm going to come back and overwrite that with a different color. Okay, so let's put all of our forces here in blue. Those are our coordinate directions. Okay, so what are all the forces? Well, we have reactions, and this is a Clevis connection, right? Like I said, there's definitely, we're pinning the position. It can't move around. It's not like a slide or anything. So there's a reaction components in X, Y, and Z in general. And then there's also the only rotation that's allowed is about the x-axis. So that means we have to have a moment, a reaction moment, like about the y-axis and about the z-axis to prevent those rotations. Okay, so all of our forces and moments on the system here is our, let's just use R for the reaction forces. I don't want to confuse, I'm going to use C for the moments, the reaction moments. Okay, this is the reaction force in the Z direction, then we have a reaction force in the Y direction. Okay, we also have the weight, mg. We also have down here at B, we have the tension in the cord, That's perfectly horizontal. Okay, and then we have those couples, or the moments, the reaction moments. Now I'm just going to assume they're in the positive coordinate directions. So for y, that's this way. I'll label that as the cy. Right? It's also like couple, right? It's convenient. And then in the z direction, it's that way. Okay. So I'll do it like that. That is c sub z. Okay, and then there's no moment, reaction moment in the x because we do allow rotation about the x-axis for a clevis connection. With this, and now remember, this reference frame, these coordinates are going to move as the bar rotates, right? And maybe if it were to go this way, it would also move with that. So we're allowing this reference frame to move with the body, and our equations are set up for that. So that's perfect. Okay. So let's just make some notes about this. So we have our reactions at the clevis C. We have Rx, Ry, Rz. These are our forces. And we have Cy, Cz. These are our moments. It allows rotation about x only, which is why we don't have a Cx and we do have the other two. Okay. Now, let's get into kinematics as the next step. Okay. What are we going to do in kinematics? Well, it's always good to relate the angular velocities and angular accelerations. We're going to do that. And we also often want to look at the angular acceleration of the center of mass of the body, and that's because that's going to be showing up in our equations of motion. So we usually want the acceleration, the translational acceleration of g, and then we want the angular velocity and acceleration of the body. Okay? So we'll write it like this. Now first we have to write so this is our coordinate system. We want to write everything in, right? Well, this omega s is straight up on the page, right? That is the axis of rotation for omega s. Okay, but that is not in our coordinates. We got to then project this into the components of the x, y, and z. Okay, in fact, this only has y and z components. It has no x component. And well, if that's beta, then through some triangle analysis, that's also beta. Okay, so we can make like a little triangle out of that. So the z component is going to be the sine beta, omega s sine beta, and the y component is cosine beta times omega s. Okay, so this is before we get into any of our relationships. The omega of the shaft, or the omega of the secondary reference frame, is its magnitude, and it's actually in the minus j hat direction. Do you see how this direction here, that component in the y direction, is actually going up towards a, which is negative j hat, as we've defined y there. So this is minus cosine beta j hat, and then it's in the positive k hat direction. So sine beta k hat. Okay, and so this now is the rotation of the secondary, right, which is the shaft, in the x, y, z body fixed coordinates. And that's where things get tricky, so got to be careful with that. Okay. Now the other rotation that it's going to show up here is what is the rotation of the body with respect to the shaft. Well, that's imposed by the problem statement to be 0, right? We want to know the tension to keep this from rotating at all. So yes, the shaft is rotating this way, and the rod could rotate that way, but we want to make there no rotation as from an observer standing on the shaft here, right? So if I'm an observer looking up here, I see no rotation of the rod, even though it is rotating this way from an observer down here in primary. Okay, so we are imposing that this is 0. Imposed by, well, the chord being there, but it's imposed by the problem statement, really. Okay, so now we're prepared to actually get into these dynamical, or these kinematic relationship, right? Which is the angular velocity of the body is the angular velocity of secondary plus the angular velocity of the body with respect to secondary, which we already determined that this one is 0. All right, which is right there. And then this just is omega s. So omega s minus cosine beta j hat plus sine beta k hat. All right, so then we make a little note to ourselves. When we get to our Euler equations, omega x is 0. There's no I hat component. Omega y is minus omega s cosine beta. And omega z is the k hat component here, positive omega s sine of beta. Okay, that's just the angular velocity. Now angular acceleration of the body. Angular acceleration of the body, that's omega dot. Omega vector dot here. All right, that's what we're going to plug into our Euler equations when we get there. This is omega of secondary plus, sorry, not omega, alpha of secondary, so angular acceleration of the body with respect to secondary, plus the cross product of secondary's angular velocity with the relative angular velocity of the body with respect to the secondary. Okay, let's see now. Alpha s, right? That is only if omega s is changing in time, and that's assumed to be constant, right? Which I might not have specified in the problem statement, but it is true. Okay, so omega s equals a constant that we don't know, but it is just a constant specified. Alpha bs is, well, we already, well, if omega bs is 0, it's also 0. Well, this could be changing in time. That might just be the snapshot, but this is in all time, right? Right, and that what we're saying here is the chord is always keeping it from moving. Okay. So again, by chord. Imposed by chord. Okay. So then let's look here. Omega s. Okay. Oh, look at that, right? Omega b s shows up, and that is 0. So we don't need to calculate anything here. This is 0. And this tells us that, and this is really a 0 vector, it has 3 components. This tells us that no matter what, omega dot is 0, right? And so that's omega dot x equals 0, omega dot y equals 0, omega dot z equals 0. All right. Last thing we say we often do in these kinematics is what the acceleration of the center of the mass is, translational acceleration. Well, that's fixed, right? That's the center. We're pinning the slender rod in the clevis here at the center of mass of the rod, and so that can't move translationally anywhere. That's a fixed point. Fixed point by observation. Fixed point in any coordinate system, right? Well, from the primary's perspective or secondary, it's not moving anywhere. Not accelerating anywhere, at least. Okay, so now we're moving into the equations of motion. Going to keep our work handy here from the first page, especially that free body diagram. Okay. Because we're moving into the equations of motion. And let's write all of them out. Then we always start with our translational version. Sum of the forces equals the mass times the acceleration of g. Well, we just said that equals 0. So this often is a very useful relationship, but this tells us that we just have a balance of the forces. And this would allow us to solve for Rx, Ry, Rz once the tension is known, but that doesn't help solve for t. Okay, so what we're going to do is move into the moment equations and just know that this is there as tools if we need it, but we're expecting this not to help. Right? It might show up later that we need to have these relationships because these reactions show up in our moment equations. But going into it, if we choose this point to do the moments about, then none of the reactions contribute to that, right? And so then these equations really are there to solve for Rx, Ry, and Rz if we wanted to do that, right? Okay, so we're going to move into the Euler equations, making note that this isn't going to help us achieve our task of expressing the tension in the cord in terms of the known quantities, or the given quantities. All right, so our 3 Euler equations, we'll just write them out, cancel things out, and see where to go from there. All right, we got them all there. So now let's go through here and see what we have is 0. Okay, come to here, and we notice that we've already done all the work, right? So omega x itself is 0, all of the time derivative is 0, and then omega y and omega z, we have their components. Those have an omega that's related to the shaft rotation rate, and then the cosine and sine projections. So all of these terms are 0. What else is 0? Omega x is 0. Okay. We also have, from earlier, because it's a slender rod, that the moment of inertia about the y-axis is 0. So that's this one right here. And, well, this one too, but that whole term is already 0. Okay. So let's then, step 4, the last step here is to solve the system of equations. Well, we need to analyze what these left-hand sides are. So let's go back to the Freebody diagram and take this one by one. Okay, so let's say, and we're going to sum moments about the center of mass, right? That was the choice there. So it looks complicated, but look, right? Anything that has its line of action right through G here is not going to contribute. So the only things that could possibly contribute a moment are the tension and our 2 reaction moments, which are already obvious where they act, right? So CZ acts about Z, CY acts about Y. Tension now, right? T is going to have is going to contribute. Let's see, only in the what direction is that? What plane are we in? Yeah, only in the x direction, right? This T is sitting here in the YZ plane. All right, maybe go back and look at the original picture where I didn't have to draw, right? This tension is there. It has components in Y and Z, but no component in X. Right, so what we need to do is the the normal direction to the T force, and then which is straight down here, and then wrap it in the T direction, right? Okay. So we can get to T, the tension, from the mgx equation. Okay. So it looks like this. I think we're gonna need to draw. Let's draw a picture for this, okay? So what I'm gonna do is take our free body diagram and just kind of zoom in on a section of it, which is just this lower section from G, or I called it C here, down to B, and then the tension is acting here. Okay, where is that beta angle? Well, that beta angle is right there. Okay, that we can use in our final answer, by the way. Okay, and so to get to, and then this is L over 2, half of the length from C to B. Okay, so to do our cross product, we need to know the perpendicular distance to the line of action of the force. Okay, which is this distance here, so that's going to be L over 2 times cosine beta. All right, and so then the cross product is L over 2 cosine beta, which is that position vector there, wrapped into the T direction. I can't do it without blocking here. So my fingers are pointing down, wrapping it that way, and my thumb then points you know, in the I hat direction. Actually, it's in the negative I hat direction, right? Okay, let's go back to the original diagram here, right? So we're basically going down here, wrapping our fingers there, and your thumb should then point kind of into the page if you do that. Okay. So having said all that, we now take this equation here and write the results down here. Okay, so this is now, we said it was in the negative I hat direction, so it has a negative component. L over 2 cosine beta times t. Right, so there's your moment arm times your force, and we determined from the right-hand rule that it was negative. Okay, so now the right-hand side of this equation is omega y, omega z, I z z. Okay, and these we determined before. Omega y was negative omega s cosine beta. Yz is positive omega s sine beta, and then Izz was ml squared over 12. And you're right, I think we can solve for t here, right? So now t then equals, well, look here, cosine beta, we have one of those on each side. Anything else, there's a negative on this side and a negative on that side, so the negatives cancel. We'll divide by L over 2. Okay, so over here we'll have an omega s squared. We will have an m. Oh, and one of the L's cancels. Okay, so that L from that side cancels the squared there. So we'll have an L. There's an m omega s squared L sine beta. And then what is the factor here? We have a 1/12 and a 2 gets multiplied over, so this is 1/6. And that is it. Okay. Now, okay, that's it. All right, that ends it. But now, if we analyze this equation, right? What does this equation tell us? This equation tells us that the moment, the only moment about the y-axis here is potentially cy. Okay, well cy, and then everything on the right-hand side is 0. Okay, so there's no moment in the y direction, and then the only thing that could possibly in the z direction for a moment was cz, and that also equals 0. So those might not be of a surprise when we look back at the original system here, right? What would be forcing the system right now to have that, any required reaction moment about these other directions. Okay, so that wraps up this second example. And all that's left is now taking all of the whole rapid semester's amount of work here